Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Welcome to Lesson 22, Modeling an Invasive Species Population. Invasive species. What is an invasive species? Well, that is something that is not supposed to be in a certain location on our planet. And it got there somehow, usually by us humans. And then once it's there, it does not have any natural predators, and it just wreaks havoc on the population of its prey. So that's what an invasive species is and does, basically. So here's a classwork mathematical modeling exercise. The lionfish is a fish that is native to the western Pacific Ocean. The lionfish began appearing in the western Atlantic Ocean in 1985. This is probably because people bought them as pets and then dumped them in waterways leading to the ocean. Because it has no natural predators in the area, the number of lionfish grew very quickly and now has large populations throughout the Caribbean as well as along the eastern coastline of the United States and the Gulf of Mexico. Lionfish have recently been spotted as far north as New York and Rhode Island. The table below shows the number of new sightings by year reported to NAS, Non-Indigenous Aquatic Species, which is a branch of the U.S. Geological Survey Department. Okay, so this table started in 1985 and it goes all the way to 2010. Number of new sightings in 85 was 1, in 92 there was 2, and in 95 there was 3, and so on, and so on, and so on. So they want us to fill in this table. Let's complete the table. So in 1985 there was 1 new sighting. Total number of sightings, 1. Okay, so 1. Total number of sightings, well, if there was 1 in 1985 and then another one in 1992, notice it took 7 years until someone spotted another one. Now that's 2 sightings. In 92 to 95, in those 3 years, there were 3 sightings in 95. None in 93, none in 94, but in 1995 there were 3 sightings, so that's now a total of 5. 1, 2, 3, 4, 5, 6. Plus 6 is 12, plus 25 is 37, and we're going to continue this table that way. Okay, so 37 plus 50 is 87, plus 45, 7 and 5 is 12, carry the 1, 9 and 4 is 13, 7 plus 2 is 9, 5 plus 3 is 8, so we're up to 189. 9 plus 3 is 12, carry the 1. 9 plus 4 is 13, carry the 1. We're up to 232. Is that right? Time out. Okay, 2 plus 1 is 3. 3 plus 5 is 8, and bring down the 2. 6 plus 3 is 9. 8 plus 8 is 16, carry the 1, 2 plus 1 is 3, plus 1 is 4, 3 plus 9 is 12, carry the 1, 7 plus 7 is 14, carry the 1, what did I do wrong? 5, 6, hang on, 7 and 7 is 14, carry the 1, 469, 569, 642. 7 plus 2 is 9, 6 plus 4 is 10, carry the 1, that's 7, 7 plus 6 is 13, and 9 plus 2 is 11, carry the 1, 1 plus 4 is 5, 3 plus 3, 6, 1 plus 1, 2. So from the 1985 all the way up to 2010, inclusively there were 2,651 total sightings. So it says complete the table by recording the total number of sightings for each year. So we just did that. Okay, page 2 brings us to number 2, and it says to examine the total number of sightings data. Which model appears to be a better fit for the data, linear or exponential, and explain your reasoning. So we'll go back, and here we go. So why is it going to be linear or exponential? Well, the number of sightings, 85, 92, 95, 96, 2000. Let's give this some thought. Now, when dealing with real-world data, sometimes it doesn't always fit the plan exactly. And you learned in prior lessons that if our X number of years increases by 1, and we have some type of constant growth, then it's linear. If this increases by 1 and it's got some sort of growth that's equal but increasing by a common quotient, then it's exponential. In this situation, we aren't going 85, 86, 87, 88, but in the real world, we can still fit this. This is going to be more like a best fit, okay? So which model appears to be a better fit, and it says it right there. So we're not looking for exact, we're looking for a better fit, we're looking for a best fit, linear or exponential function. Okay, so going back to look at the data, we see that it goes 1, 2, 5, 6, 12, 37, 87. Looks like it's almost starting to double here. 4, 6, 6 to 13 is like double. And then 13 times 2 is 26. So it looks like double, double, double. So it's definitely not linear. So I would rather say that it would be exponential before saying it is linear. Okay, so exponential. For example, the total number of sightings appears to have doubled each of the last 3 years. So number 3 says to make a scatter plot of the years versus the total number of sightings. Okay, so here's our data. So I need to have a line down here that increases so that it fits. So what I generally would do is take 2010 minus 1985 and say, well, that is 25 years. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 3, 4, 5 is out here. There's only 21 here. So I might want to go in multiples of 2, where this would be 1985. Let me fix that. So let me put 1985 here. So you put a break here and say this is 1985. And this is 87, 89, 91, 93, something like that. 95, 97, 99, 2001, 2003, 05, 07, 09, 11, 13, something like that, so it fits every 2 years. So now we can plot these points. 1985, number of sightings got pretty large as well. So we need to scale this up, and the largest sighting was 2,600. So if we made this 3,000, and that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's go an even number and put 3,000 at the 12th one. So at the 6th one, 1, 2, 3, 4, 5, 6 would be 1,500. The third one would be 750. And 3 goes into 750 250 times. So each one is 250. So this is 250, 500, 750, 1,000, 1,250, 1,500, and so on. I won't mark them all because it'll get messy, but you get the idea. 1,500. Let's go halfway between here. So adding 250, there would be 2,000 here. 2,500 would be here. and 1,000 would be here. Just to show a few. And total number of lionfish sightings, you want a title. Total number of lionfish sightings. There's our title. And this is the year down here and sightings. Number of sightings. Okay, so you want to label your x-axis, your y-axis, and you want to have a title. So now we're going to make a scatter plot. So I guess I'll use, I don't know, red. Okay, so in 1985, there was 1. Well, that's pretty close to 0 down here, right there on the line. In 92, there was 2. Here's 92, there's 2, so that's still right here. In 95, 93, 95 is here. There were 3. Oh, there's only 1 here. So 1, 1, 3. Again, it's very hard to see any difference of 1 when you're going up to 250 here. These are all of the same. 96 or 95, there were 3. 96, there was 1. So I dropped down a little bit there. 2000, there were 6. Here's 2000. 99, 2000 would be halfway in between. And there were 6, so just a smidgen higher, but not much. So nothing has changed really here. There's very few sightings. Where was I? 2001, 25. So finally we're getting 1/10 of the way up. 25 is 1/10 of 250. 2002 there was 50. So 2001 is here, 2002 is here, that 2002 there were 50, so that's a little bit higher. It's 1/4 of the way up, or a 20% of the way up, I guess, 1/5 of the way. 2003, which is here, we're 45, so right about here. 2004, there was 57, which is about there. And 2005, there was 43, it went down a little. 2006, 51. Actually, that's 2007. I'm going every other one, so let's move that halfway, right about there. 2007, there were 186. So 186, we're starting to climb now. 2008 is here. 173 might be about there. And 2009, that's when it jumped up a bit to over 500 to 667, so now we're here. And then in 2010, which is right here, we went all the way up to 1,342, which is about here, I would say. So it's slowly rising, and all of a sudden, boom, exponential pop. Okay, so there's your scatter plot. 4 says, based on the scatter plot, either revise your answer from exercise 2 or explain how the scatter plot supports your answer from exercise 2. We said it was exponential, and it's definitely not linear, so let's stick with exponential. So obviously answers will vary here. If you said linear, then you would have to make your changes. If you said exponentially, the choices you made, the reasons might be different as well. So these answers will vary, but here's an example. If students responded in exercise 2 that an exponential model would be a better fit, then the scatter plot supports their initial response since the data points appear to form an exponential curve. If students responded that a linear model would be a better fit, then they should revise their initial response and say that an exponential model would be better for this data since the scatter plot looks like an exponential curve. Number 5 says, on the scatter plot, draw a smooth curve that best fits the data. So if I drew a smooth curve now, then it's going to come up like so. It's going to curve, and then it's going to somehow curve up like so. Again, your points will not be exactly on the line, but they should be close. Okay, page 3 brings us to number 6, and it says, from your table, calculate the average rate of change. Average rate of change. And the total number of sightings for each of the following time intervals, 1995 to 2000. So let's go back. So in 1995 to 2000, now remember, rate of change is f of x let's see, f of x, or, well, let's just call it y for now to avoid some more confusion. So it is, all right, so rate of change is your change in your y over your change in your x. So delta y over delta x, which is y2 minus y1 over x2 minus x1. So when we're going from 2005, now I forgot the years, 95 to 2000, so y2 is 2000, I'm sorry, that's x. Whew. All right, try that again. So x2 is 2000 minus 1995, and our y's in 2000 were 12, and our y in 95 was 5. So it's 12 minus 5, which is 7, over 2000 minus 1995, which is 5. And that's 7 over 5. So we're going to put that in decimal form. So if you take 7 divided by 5 and hit enter, you're going to get 1.4. So this is 1.4. Average rate of change between those 5 years is 1.4 fish per year on average. Now we're going to do the same for 2000 to 2005. So let me just erase this. Okay, so 2005 minus 2000. In 2005 we had 232. Minus 2000 we had 12. 232 minus 12 is 220, divided by 5. 5 goes into 22 4 times, the remainder of 2. 5 goes into 24 times, so my answer is 44. So there was an, oh, wrong way. There was an average rate of change of 44 sightings between the year 2000 and 2005. It's a lot more than 1.4 sightings on average, isn't it? Okay, now we're going to go to 2005 to 2010. So one more time, I'll erase these values and do 2005 to 2010 as my denominator. 2010 minus 25, 2005. 2010, there was 2,651 sightings, and in 2005 there was the 232. So 4, 11, 11 minus 2 is 9, that's a 4 now, 4 minus 3 is 1, 6 minus 2 is 4, and 2 minus 0 is 2, so there's 2,419 divided by 5. 5 goes into 24 4 times, that's 20 with a remainder of 4. 5 goes into 41 8 times with a remainder of 1. 5 goes into 19 3 times, which is 15 with a remainder of 4. And 5 goes into 4.8. So let's just say 484. It's actually 483.8. I'll put that. 483.8 was our average rate of change between 2005 and 2010. So the average is like 30 some times greater here and 11 times greater here, over 11 times greater there. So number 7 says, how do the average rates of change help to support your argument of whether a linear or an exponential model is better suited for the data? Okay, if the model total number of sightings was growing linearly, then the average rate of change would be constant. Instead, it appears to be growing multiplicatively, indicating an exponential model. Number 8 says to use the regression feature of a graphing calculator to find an equation that models the number of lionfish sightings each year. Okay, so now we're going to use our calculator, and we're going to go to Stat, Edit. Okay, so there's stuff in there, so I'm going to go back to Stat, and I'm going to clear the list. So I'm going to press 4. clear L1, comma, clear L2, enter, done. Now when I go stat enter, they're blank. And we're going to put our L1s as our years. And we don't want the actual year here, we want to put year since. So 1985 would be 0. 1992 would be 7. So you have to be careful to do that. 1995 is, we're talking years since 85. So how about I do that with my pen? And let me do it on the original, it's larger. So if 1985 was year 0, 86, 7, 8, 9, 9, 91, 92 is 7 years later. That's year 7. 85 to 95 is 10 years. To 96 is 11. 2000 is 15 years. 2001 would be 16 years since 85. You get the idea? 17, 18, 19, 20, 21, 22, 23, 24, and 25 years since 1985. Okay, so now that that's all done, we can just enter them quickly in the calculator. So we just we did 7, so now we're on 10. So 10, enter, 11, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So then I always check. Last one was 15, so then I come over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 entries. L2 is going to be our cumulative values, total sightings. So would it be total sightings or would we use number of new sightings? I would say number of new sightings. You don't want to count things more than once. So L2 is going to be 1, L1, 1, enter, 1, 3, 1, 6, 25, 50, 45, 57, 43, 51, 186, 173, 667, 1, 3, 4, 2. Okay, make sure they match or you'll get an error saying mismatch. Okay, so we have all of our data. Then we go stat, calculate. And what are they asking us to do? Let's go back now. Use the regression feature of the graphing calculator to find an equation that models the number of lionfish sightings per year. Okay, so we're going to do a linear regression. So that is a plus bx, which is 8, I believe. Enter. Using L1, L2, calculate. And then we go to y equals. Okay, so then we press vars, statistics, arrow over to EQ, and hit enter. And that entered our equation here. Now if I zoom 9, that will zoom statistics. Okay. And I don't see anything here. So I have to go back to my y equals. I want to turn plot 1 on, so I'm graphing statistics. Now I hit zoom 9, and there is our data. Okay, and as you can see, it looks like this graph right here, doesn't it? Bunch of data down near 0, and boom. There's our linear regression. Obviously it didn't fit very well, it just went straight through it and it's nothing anywhere near. So that was not a good model. So now we're going to try an exponential regression. So now I'm going to go back to my home screen and I'm going to press stat, calculate. Now we're going to do an exponential regression, which is number 0. Or 10, press enter, enter through. We're using L1 and L2 for our values. And now that says y equals a times b to the power of x, where our a, which is our y-intercept, is 0.17, and our b, which is our quotient, common quotient 1.3575 rate of change. So now when I go to y equals and come down here and press vars 5 EQ, enter, then it put that exponential equation in there. There's that decimal to the power of 6. Now when I hit zoom 9, it is going to graph the linear, and then it should graph the exponential as well. And there it is. So let me change my window. Well, no, I don't need to change the window. You can see that the line came along here and then it curved and started going up. So we definitely know the exponential is a much better fit than the linear. Now let's answer these questions. So what was the equation? That's what it's asking. So if I go back and I go stat calc 0 for my exponential and press enter through, it's easier to see it on this screen. So there's my answer. So now I'm going to enter it down here. So my equation is going to be, for the exponential, it's going to be y equals well, let's see, that is 0.1748. So I would say 0.1748, that's my y-intercept, times my b, which is 1.3575. It's an approximation, right? So I suppose I should not have an equal sign here. Let's change that to an approximation. And that's a decimal. And that's going to be to the power of x. If it were linear, then we just go back and we press stat, calculate 8 for linear, press enter, 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 and we get y equals negative 285.679x plus 27.9685. Okay, but that was a really bad, oh, that's negative, by the way. Okay, I need to fix that. I didn't even put an equal sign or anything. Move this over here. Move that to there. And y is approximately negative 285.679 plus 27.9685. Okay, so once you have a model, now you can use it to predict future. So now it says predict the total number of lionfish sightings since, or by the end of 2013. So I want to go back to my table. Keep in mind what these values are. So 2013 would go here. And how far is that from 85? Well, it's 3 more than 25, or 28. So we want the point 28, comma 2013. So I'm going to get rid of my linear equation and then show the exponential again. There it is. And now I'm going to try to figure out what it's going to be in 2013. And let's get rid of these entries. So I want to enter 28. And I got an approximation of 911. But that's lower. So let me go back to my graph and hit trace and see what these values are. Okay, that is 1,342. That's when x is 25. When x is 28, it should be more. So I'm trying to figure out what's going on here. Let me do something here. Let me clear this, and let me clear this, and redo the calculation. So I'm going to calculate exponential regression from L1 and L2. And there it is. Now I'm going to go to y equals and press vars 5 EQ, enter, graph. I'm just double checking my work here. Okay, it is that one. So then when we go out to 28, okay, so this is not fitting very well. It's not getting steep enough, fast enough for some reason. So when I go to second graph and press 28 in, it does give me 911, but in actuality, it should be more than that. Okay, I double checked my numbers, but they're all correct, so I'm gonna just go with this, but it should be higher, but my graph didn't fit the data really well. But anyhow, so when we use the exponential function, the sightings was 911. Linear, use your model to predict the total number of lionfish sightings by the end of 2013. Oh, okay, so we want to add that 911 to what we've already cited. So the 911 would be right here. So let's just go back to the original. And then when I come down here, then we're going to put 911 here. And then add these up. So that's going to be 2. 5 plus 1 is 6. 9 plus 6 is 15. Carry the 1. So it's going to be 3,562. That makes more sense now. So using exponential, it's going to be approximately 3,562 total sightings. Not just the number of sightings that year. Okay, just double checking. 3562. 3562. Okay, so then it said if we use the linear model now, so let's do that. So let's go stat, calculate 8 for linear, and enter through. And get this. Then go to y equals, clear the exponential, and paste by pressing vars 5 for statistics and EQ. That's how we paste it. And now we hit second graph and press enter. There's the approximation for the linear, 497. So now if I go back here, I'll do this one in purple. That would have been 497 if this were linear. And then we add that to here, that'd be 8. 9 plus 5 is 14. And 6 and 4 is 10, plus 1 is 11. It'd be 3,148. If it were linear, total sightings. Okay, and then when I graph that, it should show the line going through again. Okay, so obviously the exponential, there was 400 and almost 20 more, 400 and some more. Exponential is closer. The actual number of sightings was 3,776, so my exponential is closer. Does it seem that your model predicted the accurate prediction? Explain. We are off by a little, so if we took 3,776 and subtracted 3,562, then we'd get 4,1. We're off by 214 fish. 214 fish, that's messy. 214. So 214 when we're talking about total 3,776. It's fairly close. But I think it's close enough to say yes. It's better fit, of course, than the 3,148, which was off by over 600. So exponential definitely was a better fit. Page 4 brings us to the end of lesson 22. Go to your problem set.